Hi, in this third video on the topic of counter sets, we are still in the setting of one-dimensional counter sets. We revisit some concepts from previous video and then continue with what are called fat counter sets. In the previous video, we described a very general phenomenon that allowed us to obtain counter sets of dimension 1 and of dimension 0. But actually there's an easier way to get such sets. Recall the basic construction that if you remove from the middle intervals so that the remaining length of each subinterval is lambda times the previous one. So you fix this lambda, this ratio, and that is between 0 and 1/2. And if you remove your middle intervals so that the remaining subintervals have length lambda percent of the previous step, then you obtain a counter set whose Hausdorff dimension will be log 2 divided by log 1 over lambda. With the lambda equal 1/3, of course you have the famous counter set whose dimension then becomes log 2 over log 3. Now if I want to obtain, so of course when lambda is between 0 and 1/2, then this dimension that we have is some value between 0 and 1. And you don't have the endpoints included. So it doesn't include 0 itself and it doesn't include 1 itself. So per se, this construction does not produce a counter set with Hausdorff dimension equal to 1, but we can get as close as we want. And that's actually the point behind a modification that will allow us to obtain a counter set of Hausdorff dimension equal to 1. And the way we do it is you start off with some lambda. Let's say you have lambda 1 in the initial step. If you continued with this lambda 1, of course you would get a counter set with Hausdorff dimension log 2 divided by log of 1 over lambda 1. But then what happens in the next step, you revise your construction. You say, okay, wait, I'm actually not happy with the choice of lambda 1. I want to do it in a way that I get a little bit in my intervals, so that now this becomes lambda 2 times lambda 1. So it becomes lambda 2 times the previous one. So let's remove these to avoid confusion. If you continued with new lambda, which is lambda 2, then you will end up in a counter set which will have Hausdorff dimension log 2 divided by log 1 over lambda 2, and this dimension will be bigger than the previous one. I'm using some not so difficult fact to believe that I'm beginning this lambda 2 construction. Suppose that I keep lambda 2 for the rest of this construction. Why do I get a counter set with Hausdorff dimension this much? It is because it's basically the same whether you start off from 0 and continue with lambda 2, or you start off with any other interval. By similarity of the structure, whatever proof you have, you just scale your numbers towards the length of that interval you begin with, and you will end up with that set. So what I'm saying is that if you repeat counter construction with a fixed ratio from any interval of any length, you will end up with a counter set with this dimension. So here, my starting interval with lambda 2, I'm assuming is here, and from this point on, if I continue with lambda 2, I will end up with a counter set with this dimension. But then I'm again not completely happy with lambda 2, because that will again give me some number less than 1. So in the third step, I improve that even more. So I do this in such a way that I end up with sorry, that won't be it. So the next step would be that I have this green divided into two parts, and if I were going to continue with lambda 2, that this would be lambda 2% of the previous green interval, but I have replaced it with lambda 3, so something a bit larger. And again, if I kept doing this construction with lambda 3, I would get a set with this Hausdorff dimension, which is again strictly bigger than the previous one. If I repeat this, the counter set that I will end up with will be a counter set that contains all the copies, all the other counter sets that I would obtain by continuing with one of these lambdas from the finite step all the way to the infinity. So, for example, if I kept lambda 2 all the way down here, I would get, let's say, a counter set C2. But now that I have replaced lambda 2 with lambda 3 and subsequently even larger ones, this will be contained in whatever this alt counter set I get with the adaptive construction. So in particular, dimension of this will be larger than dimension of that. So that I know that I will end up with a counter set with this construction, and dimension of that counter set will be bigger than each and every one of these numbers, because, well, I said C2, but you can repeat it with any I. So if at step I kept the ratio lambda I forever, from that point on I again end up with a counter set, but that is smaller than the counter set I get now, because I get larger intervals when I improve on my lambdas. So that dimension of C will be bigger than dimension of the Ci, which is log 2 over log of 1 over lambda I. But if I keep my lambda converging to 1, so if I do it in a way that if my lambda i's converge to 1/2, then dimension of this counter set I get will be equal to 1. Of course, there are things to be checked. For example, is this a sustainable construction? Can I keep it forever? Do I not run into intervals growing too much and overlapping? Well, that's because these lambdas are just ratios. So by its construction, you're avoiding any such thing. About closeness and compactness of this set, similar arguments to other types of counter constructions will work. And then, well, the most important part for us was this one. So this way you get a counter set of dimension, Hausdorff dimension, equal to 1. On the other hand, if you decrease your lambdas as you go, you retain less of the intervals at each step. So you start with the ratio lambda 1, but then you decrease it to some smaller ratio, and then you again decrease it forever. And that way you can end up with a counter set with Hausdorff dimension 0, because now your lambdas converge to 0. Okay, so that we already knew from previous session that there do exist counter sets with full Hausdorff dimension. The topic of fat counter sets, which I now begin to talk about, is to obtain. So if we try to give a definition, a fat counter set is a counter set with positive length. So the fatness is saying that, well, first of all, it has Hausdorff dimension 1. That means H1 of the C. We know that H1 is just Lebesgue measure. That's famous that Hausdorff measure Hn equals Lebesgue measure in Rn. And we want this to be positive. So fatness, by definition, is this condition of positivity of length. We will talk about the most famous fat counter set, but before that, let's talk about the surprising fact about counter sets and why they are amazing. Counter sets, and that includes the fat ones, are nowhere dense in R. And that means, well, they are not dense means their closure, which equals C itself. So notice that closure of a counter set is just the counter set itself because it's closed, and it is not equal to R. So C is not dense in R. But nowhere dense means that even if you are concerned only on some possibly very small interval, even there the closure is not all of A, B. So not only they are not dense in the whole R, they are not dense in any subintervals. And that is easy to see by constructions of counter sets, because if you give me 2 points, A and B, I know that when I go further in the steps of the construction of counter sets, I will be looking at intervals whose length, say, are less than B minus A divided by 100. So I'm being very cautious here, but maybe half, even 1/2 or 1/3 does that too. But definitely then that would mean that if this is one interval in the construction, well, 1/100th of that will be very small. And let's say this. There will be some removed intervals from within A and B. Not having a removed interval would mean that there is some interval that contains all of A, B. But then that the length of that interval will be A, B minus A, bigger than at least B minus A. But now we assume that we are so far in the steps of the construction that the intervals we're looking at are really tiny. In particular, they cannot be comparable to the full length of A and B, so there will be some gaps removed, definitely. And, well, the closure of this set, ultimate counter set, will also miss this gap, and that's where it will definitely not be dense. So you're looking at a set that is not dense anywhere. In that sense, it's even less than the rationals, which are dense everywhere. On the other hand, rationals are very small from the point of measure because they have measure 0, even Hausdorff dimension 0, so they are way, way small from the point of view of Hausdorff measures. Yet, they do have positive length, and that's kind of counterintuitive. How could they be not anywhere at the same time have a lot of claim inside inside R. But, well, it's a fact of life that such sets do exist. The famous example of a fat counter set is called Smith-Volterra-Cantor set, and there is a Wikipedia article dedicated to this, and also if you just Google it, there are many other articles people have written about this set. It starts again by the unit interval 0, 1. The next step is, it will be 0 and 3/8, union 5/8 and 1. So from 0, 1, instead of removing the middle third, you have removed 3/8 to 5/8. So that means an interval of length about equal to 1/4. And you can precisely describe what happens in the next step for the removals, but, well, why do that if we can describe it more easily? So you remove so that the length, so you remove from the middle of the intervals, but now you want this property that the length of remaining intervals, not the removed one, whatever remains, intervals, is 1/2 to the power 2n. So in the first step, when n was equal to 1, we had something is not matching up here. Oh, okay. Actually, I mixed up this, the remaining versus the removed. So the length of the remaining intervals will be this little ln equal to 2 to the power n plus 1 over 2 to the power 2n times 2. That is, we can put plus 1 in the numerator, but this is maybe easier to not confuse. And with n equal 1, you see this is 3/8. The length of this interval, the length of this is equal to the previous one. So that just property ln completely and uniquely determines how this construction should proceed. And similar to how we prove that the counter set, the 1/3 counter set has measure 0, you just add up the length of the remaining intervals and just compute what is remaining from the interval. So by calculating the L1 measure of the set that you will get will be actually equal to 1/2, which is in particular positive. So this set will have about 1/2 of the full length of the interval you started with. And this last fact is pretty easy to prove. The Wikipedia article gives a more general result. So it says that, suppose, yeah, this is where I mixed this with the example. Suppose intervals of length a to power n are removed from 0, 1 at each step. So n equal 1, that means a, so you remove an interval of length equal to a, and then you remove an interval of length equal to a squared, and so on. So now this time we assign the length of the remove interval. So the removed interval will have length A, and in the next step from these, the removed intervals will have length A squared. So the gaps are described this time. So we'll be here, again A squared here, and so on. And if you continue this way, it's easy to see the length of the counter set at step n. So like the usual counter set, because you keep doubling, you have 2 to power n many of such intervals, of these gaps, and each gap has length a to n. And if you count, you will see that there is this additional thing. So n from 0 to infinity will be the length of the gaps. So this is the length, the total length of gaps. So you do 1 minus that quantity, and that becomes equal to 3a, 1 minus 2a. So this becomes the measure of the set, the counter set you obtained this way. And here a is something between 0 and 1/3. If you take a to be 1/3, you are left with measure 0. So this is like the usual 1/3 counter set that has measure 0. And on the other hand, when you approach 0, you get a set with measure equal to 1. Of course, it works here with the picture that the larger gaps you have, the smaller will be the measure of the counter set, the remaining parts. So all easy facts to confirm, but again, there is non-trivial ideas behind them. This set is famous for the construction of the function out of it, which at some point we will talk about counter functions as well, because they are super important for the theory of sublevels functions and calculus in general. Okay, so that's Smith-Volterra-Cantor set, which has positive measure. But again, with so much flexibility, there are endless number of ways in which you can produce counter sets that have positive measure. As we have seen from previous discussions, for example, here, we already had seen a set with Hausdorff dimension 1, but now by some adjustment we were able to also produce a new way in which we obtain a counter set with dimension 1. So it's kind of a thing that you learn. It's a game, and once you know the rules, you can always devise and adapt things to your needs, and that's what happens in your research papers. You want a certain counter set with certain properties, and you basically build your own, but the rules of the game are pretty much always the same. So thank you for watching this video as well. Please subscribe if you haven't. We are reaching the 300 threshold. I'm thinking about doing something special when we reach there, but I don't want to reveal them yet until we are there. Thank you.